Good morning to everyone present here. I'm Sangeeta Lakshmi, working as Assistant Professor in EC Department of R.M.K College of Engineering and Technology. Today we are going to start the second unit, that is MOSFET amplifier. Unit 2 is MOSFET amplifier. The syllabus or load line Q point. Then we are going to see what are all the biasing methods available for MOSFET. Then we are move on to analysis of common source, common drain, common gate MOSFET amplifier using hybrid pi equivalent circuit. Then we are going to see MOSFET differential amplifier. Finally, multi-stage amplifier. So what are all the topics we are going to discuss here is, first, we are going to see what is amplifier. Then we are move on to the load line and Q point. Then we are going to see different biasing methods. Today we are going to see these three topics. So first of all, we have to know what is an amplifier. See here, this amplifier contains the signal source, that is your input signal, right? It may be your audio signal or video signal. Then we have the DC source, right? Here it is load. Load is nothing but the which are the device which will consume the power. It's called as load. Example is speaker, right? Which are the device which will produces the power is called source, right? The example here is CD player. For example, if you have the public addressing system, right? Public addressing system, that is we need to speak through the speaker, right? So we that signal source which is coming from the CD player, if you are directly connected to the speaker, we could not able to hear any words from the speaker. That means the output from the CD player is not that much capable to drive the speaker. So we need some device which will amplify your signal which is coming from the CD player. So that device is called amplifier. Okay. So this amplifier must be linear amplifier. Then only we can get the faithful amplification. Faithful amplification means without any loss, we have to get the whatever the signal you are giving at the input side, that magnified version only we have to get at the output side without any loss. That is called faithful amplification. So in order to get the faithful amplification, we need linear amplifier. Linear amplifier means it possesses the superposition principle. Okay. So here why we need the DC source means from the DC source only we are getting the power. The signal will be superimposed on the DC signal so that it will be amplified, right? So you will be getting, for example, if you are giving 5 volts here, if you are applying at the input side of the amplifier, if you are getting 500 volts means the amplification, that is gain, is nothing but the output by input, right? So the gain is nothing but voltage gain equal to output voltage by input voltage, which is V naught by Vi. So V naught is nothing but the 500 and Vi is 5. So the gain is nothing but the 100. There is no unit for the gain. Clear? So this is the example for public addressing system. Suppose if you have the video signal or any image is captured by the space, that is from the satellite in space, that signal, if it is coming to the earth station, definitely it will be very weak because it has to travel through long distance. So in order to view that image, we need some amplifier. Okay. So here the signal source is nothing but you are getting the image from the satellite. Okay. So that is given to the amplifier, right? So amplified version is given to the load, which is here it is monitor, TV monitor or laptop monitor. Okay. So you can able to see that image after amplification. Okay. So many applications are there for the amplification. Next, we are going to see why particularly we have to go for the MOSFET amplifier. Because many advantage over than the BJT. In first unit, we have seen the BJT amplifier, right? So second unit, full and full, we are going to see the MOSFET. So before that, we have to know why we are going for MOSFET when compared to BJT. The first important difference is the BJT is, you know, that bipolar junction transistor, whereas MOSFET is metal oxide semiconductor field effect transistor. So the first difference is the BJT is current control device. Why it is called a specifically current control device means we know that the current collector current IC equal to beta into IB, right? So here IB is nothing but your input current, whereas in IC is nothing but your output current. So the output current is controlled by the input current. That's why it is called current control device. Whereas in MOSFET, if you are taking the drain current equation, ID equal to Kn, conduction parameter Kn into VGS, gate source voltage minus threshold voltage of the transistor, right? The whole square. So here the input is nothing but the VGS, the output is nothing but the drain current. So the output current is controlled by the input voltage. That's why it is called voltage control device. The next difference is it is bipolar. I told you bipolar in the sense the current conduction is depends on both electron as well as holes. Okay, electron as well as holes. Whereas in MOSFET it is unipolar. That means the majority, the current conduction is depends upon the majority carrier. Suppose if you have the N mass means the majority is electrons, whereas in P mass means the majority is holes, right? So the current conduction in MOSFET is depends only on the majority carrier, not both. Whereas in BJT it depends on both the carriers. And next is BJT having high voltage gain, right? Whereas in MOSFET it having low voltage gain. So when compared to BJT and MOSFET, BJT is best in terms of voltage gain because it produces high voltage gain. Okay, and also the gain is depends directly proportional to the beta, right? So the gain is directly proportional to beta here, whereas here the gain is directly proportional to transconductance GR. Okay, and next parameter is low input resistance. The BJT having low input resistance, whereas MOSFET having high input resistance. Actually, this is a required quality of any voltage amplifier. For any voltage amplifier, the input resistance must be high. This is a very good quality of any amplifier. Why means you know that voltage equal to current into resistance as per the Ohm's law, right? If you are having high resistance, you will be having high voltage. It is directly proportional, right? So if any amplifier having high input resistance means the amplifier will easily receive even a weak signal. Okay, that is a good quality of any amplifier. And next one is the BJT having high output resistance, whereas in MOSFET having low output resistance. This is also good quality of any voltage amplifier. Because if you are having low output resistance, all the voltage produced by the amplifier will be given to the load. Okay, if you are having low output resistance, right? The next thing is the BJT having that is consume more power when compared to MOSFET. So this is also good character of MOSFET. So that's why we are going for the MOSFET. High input resistance, low output resistance, and low power consumption. It requires very less amount of power. Okay, in the case of MOSFET, it is having 10 power 12 ohms. The high input resistance approximately it is 10 power 12 ohms. Okay, it's very high resistance. Ideally, we can call it as the MOSFET having infinite input resistance. This is the biggest quality of MOSFET. Okay, so because of these advantages only we are going for MOSFET. The final advantages, the BJT produces more noise, whereas a FET is less noise. Okay, so this is also a very good quality of amplifier. Okay, so these all the advantages of MOSFET we have seen. So next we are going to see what is load line, Q point in different biasing methods. So we are going to see the two different biasing methods of MOSFET. The first one is biasing with feedback resistor. The first method is biasing with feedback resistor. See here, this is your biasing, that is feedback resistor. This RG is nothing but the feedback resistor. That's why it is called biasing with feedback resistor. Okay. So we know that for the MOSFET, you are having the gate, drain, right? Gate, drain as well as source. So the current flowing through the drain terminal is nothing but the ID. Current flowing through the source terminal is nothing but the IS, which is approximately equivalent to ID only. Because the IG current always, I told you in the previous slide, MOSFET, the good quality is high input resistance. Because of the high input resistance, the current flowing through the gate terminal is 0. If it is 0 means, what is the meaning? The voltage across RG is 0. Because always the voltage equal to the current flowing through RG is nothing but the IG into RG. IG equal to 0 means again the voltage drop across RG also 0. So we can replace this circuit by this circuit because the RG is ineffective from the circuit because of the gate current is 0. Okay, so this is the biasing with feedback resistor. First of all, what is biasing? Biasing means it is a process of giving the DC supply to the transistor in order to operate the MOSFET in a active region or else saturation region or else cutoff region. It is depends upon your application. For example, if you want to use the MOSFET in a amplification purpose, we have to bias the transistor in a saturation region. This is the biggest thing you have to know. BJT always we have to operate in a active or linear region in order to act as an amplifier. But in case of MOSFET, we have to operate this MOSFET in a saturation region for amplification. Okay. Then we are going to see what is load line Q point. So load line is nothing but this is your load line. See this graph. See this graph. In this graph, in x-axis you have the VDS. In x-axis we have VDS. In y-axis we have the drain current ID. Okay. So this is nothing but the transistor output characteristic. That is MOSFET output characteristic. In this dotted line indicates that this is the transition point. That means up to here, this is called a non-saturation region. After this transition point is called saturation region. I told you, if you want to make the MOSFET as an amplifier, we have to operate in a saturation region. So, from this point to here, from here to here, this is the saturation region. So, out of this whole region, where we have to fix the Q point. Always we have to fix the Q point in the middle of the load line. So this is called as load line. Load line means it is a line drawn on the output characteristic of the transistor. Okay, here this MOSFET. So this load line will give you where we have saturation region, where we have non-saturation region. Okay. So after finding out this load line, we have to locate the Q point. The Q point will give you the two values, right? Which is nothing but the Q point means we have two values. Always if you have two-dimensional, it is two-dimensional. In x-axis we have VDS, in y-axis we have the ID. Two-dimensional means any point at two-dimensional having x as well as y, right? So here also at the Q point, we have two values. One is x is nothing but the BDSQ and y-axis we have the IDQ. Okay, so this point is nothing but the BDSQ and this point is called as IDQ. Okay, so this is the what is mean by this Q point means, see, whenever if you are applying the DC voltage in order to make it in a saturation region, the VDS as well as the ID current will be established in the circuit. Okay, so that current and voltage is called Q point voltage. Q means quiescent point. Q means it is called as quiescent point, quiescent, or it is called idle point, or it is called as bias point. Okay, why it is called as idle point means, see, for any analysis, for DC analysis, this is we are analyzing only with respect to DC voltage. Okay, for any DC analysis, we have to open circuit the capacitor, because for DC analysis, you know the reactance of this C1. Reactance XC1 equal to what? 1 by 2 pi FC1. Okay. For DC analysis, we know that frequency equal to 0. If frequency is 0 means you know that 1 by 0 is infinity. That means the C1 capacitor will produces the infinite reactance. Reactance is nothing but the resistance, right? So if it is infinite resistance means this input voltage will not going through the capacitor, right? So we have to open circuit this coupling capacitor C1 as well as coupling capacitor C2, right? Both the capacitor we have to open circuit for the DC analysis. Then only you are getting this circuit. The next circuit you are getting after open circuiting your coupling capacitor, and then you are removing RG because of IG equal to 0. I hope everyone understands this, right? Next we are going to see how to draw this load line. We have seen so far what is load line, what is Q point, right? Next I am going to explain you how to draw the load line. Okay, so for that you have to see this circuit diagram. In the circuit diagram you have to apply the KVL at the output side. So if you are applying the KVL at the output side means what? Output side means in between drain and source. Okay, this side is the output side. So if you are applying the KVL at the output side, see here the current flowing through RD is ID. So the voltage drop across RD is nothing but the what? ID into RD. This is your voltage drop. Next, you have the voltage between drain and source is what? VDS. So you have to add this plus VDS. Then it is ground. Ground means 0 voltage, right? Again, the circuit will be closing up to here. This VDD is, the positive is connected here. The negative is connected to the ground, right? This meaning is the positive of the VDD is connected to the circuit, the negative is connected to the ground. Thereby the circuit will be closed here, right? After this ground, first you are meeting minus. So you have to write here minus VDD equal to 0. Thereby here ID into RD plus VDS equal to VDD. You can consider this is the first equation. Okay, so if you want to draw the load line, we want the 2 points, right? So if you want to draw the load line, see here, this is your load line. In x-axis you have the VDS, in y-axis we have the ID. Okay, so here if you want to draw the line means we need 2 points. This is point A, this is point B. We need 2 points. So if you want to locate the point A, you have to apply, see here, if you want to locate this point A, you have to apply VDS equal to 0, right? Yes or no? At point A, the VDS is 0. So if I am applying VDS equal to 0 in equation 1, you will be getting ID into RD equal to VDD. Thereby, ID equal to VDD by RD. This is your maximum current. This is the maximum current obtained from the circuit, right? So the point A is nothing but the what? VDD by RD, which is nothing but the ID max, right? So after locating point A, you have to find the point B. So how to find the point B means, see, if you want to find the point B, you know that ID is 0, right? So you have to make ID equal to 0 in equation 1. So if you are making ID equal to 0 means you will be getting VDS equal to VDD. This is the maximum drain source voltage, right? So this point is nothing but the what? VDS max, which is equivalent to VDD. So after locating these 2 points, you have to draw the load line. So this is your DC load line. So you have to know, if you want to draw the DC load line, always we have to apply the KVL at the output side, right? You will be getting one equation. In that equation, you have to substitute VDS equal to 0. You will get the point A. Then you have to substitute ID equal to 0 to get the equation, that is point B, right? So after locating these 2 points, if you are drawing line, that is called DC load line. Clear, everybody? Right? Next we are see what is Q point, right? See, you have to take the same equation 1, right? From equation 1, you are having ID into RD plus VDS equal to VD. Okay, so here ID is nothing but the IDQ. In this equation, without substituting any condition, VDS equals 0, ID equals 0, nothing you have to substitute. The same equation, after applying KVL at the output side, you are having one equation, right? In that equation, ID is nothing but IDQ, which is equivalent to what? VDD minus VDS by RD. So this is your IDQ. Okay. Similarly, what is VDSQ? VDSQ is, it's nothing but the same equation, VDSQ equal to, you have to write VDD minus ID into RD. Okay. Here, in single equation, you could not able to find out IDQ as well as VDSQ. So, instead of using this equation, we have to use the ID equation, which is nothing but the IDQ equal to, you know that general equation, Kn into VGS minus VTN whole square, right? So, if you are using these two equations, you can easily find the Q point value, which is Q point value, right? So Q point is always located at the center of the DC load line. So this point is called IDQ. From this current equation, you can able to find out IDQ, right? After finding out the IDQ, if you are using this equation, you will find what is VDSQ. I hope everyone understand this biasing with feedback resistance. Okay. The next biasing method is voltage divided biasing. Okay. So in this voltage divided biasing method, again I told you for the DC analysis, I told you we have to make all the capacitor to, we have to open circuit, because I told you this coupling capacitor CC1 and CC2 both will be exhibiting the resistance, that is reactance equal to XC equal to 1 by 2 pi FC, right? So for DC analysis, frequency is 0. So if it is 0, 1 by 0 is infinite. So infinite means this is open circuit, because the current will not flow through the infinite resistance. So if we are removing both the capacitor, coupling capacitors 1 and 2, you will be having the circuit diagram. Here R1, then you have the resistor R2, here transistor, MOSFET transistor, here we have RD, Here RS, this is VDD. Okay, so here we have ground. All the ground is connected together. So after removing this open circuiting this coupling capacitor, you have only this circuit, right? Only this circuit. And here also we have to open circuit this source capacitor. So you have only this RS. So now I told you, no, we have to apply KVL at the output side in order to draw the DC load line, right? So how to write the KVL equation here? KVL at the output. So if you are applying the KVL at the output side, you will be getting ID into RD, right? ID into RD, because the current flowing through the RD is ID. The current flowing through RS is IS. IS is approximately equivalent to ID only, right? So what is the voltage across here? This is the drain terminal. This is drain terminal. This is your source terminal, and it is nothing but the gate terminal. So the voltage across drain and source is nothing but the VDS. So here I have to write ID into RD plus VDS plus here the voltage drop across RS is nothing but the IS into RS. Instead of IS, I can substitute ID, right? Then here it is ground. Again, this VDD you are having, the circuit will be closing here, right? So you will be getting minus VDD equal to 0. So from this equation, I am grouping ID common outside, RD plus RS equal to VDD minus VDS. You can consider this is the first equation. So if you want to locate the point A in the DC load line, I have to substitute VDS equal to 0. So if I am substituting VDS equal to 0, I will get ID into RD plus RS equal to VDD. Thereby ID equal to VDD by RD plus RS. This is the maximum current produced by the circuit, right? Similarly, you have to find the point B. How to find the point B? I told you we have to make ID equal to 0. If I am making ID equal to 0 in equation 1, you will be getting what? ID equal to 0 means 0 equal to VDD minus VDS. Thereby, VDS equal to VDD. This VDS is the maximum voltage, right? So, if you are drawing the DC load line, in x-axis you have the VDS, in y-axis we have the current ID. Okay, so in this, the point here it is A, here the point is B. So, A is nothing but the what? VDD by RD plus RS, that is ID max. B is nothing but the VDS max equal to VDD. So after locating these 2 points, if you are drawing on straight line, this is nothing but the DC load line, right? Similarly, how to locate the Q point? The same equation, one you have to take, the same equation you have to take, right? So if you want to locate the Q point, see here, if you want to locate the Q point, I told you Q point is nothing but the VDSQ as well as ID, right? IDQ. So how to find out ID? ID equal to what is the formula? It is general formula Kn into VGS minus VTN the whole square. This is a threshold voltage of the MOSFET transistor. VGS is the voltage between gate and source. So this is the VGS. The voltage between gate and source is VGS. So after finding out this ID, which is nothing but IDQ, you have to use the equation 1. From equation 1, you have to find out what is VDSQ. So VDSQ equal to what from this? You will be getting what? VDD minus ID into RD plus RS, right? So that you can able to find out Q point. Clear everybody? I hope everyone understand this both biasing methods. So here we have analyzed amplifier only with respect to DC signal, and then we are going to move on to the small signal analysis, that is we are going to analyze with respect to AC signal, that means your audio signal or video signal. Okay, thank you.